whatever views. Shit. And now I'm like, hello. And for today's stream, we are going to continue. Well, of course, we are going to continue. That's like nothing special. 220. And where were we? We were about to begin something big. Yep, we were here. We did implement implications for this. Yesterday, we were seeing about how fractions and bases are converted, which is mostly maths, and this is more assembly, and this is less assembly and more maths. So if I only get a partial idea about what they are talking about here, what the author is saying here, then it is also okay. I do not have to beat myself up for not understanding every single thing here. Yep, we did this, and now fixed point numbers for today. And I believe that rest of this book is more maths and less assembly. So even if I only get a partial idea about the things, about the topics here, then it is okay. I do not have to beat myself up for not understanding every single thing here because I have other things which will help me grow in learning about binary bits and manipulation, how data is actually stored and manipulated in bits. And the goal with this video series is to understand assembly. And this is for me, this is not for the people to watch. And why am I streaming? I'm streaming because I want to have some accountability, and that is the whole reason. And if you want to watch, you can watch. That is okay. But this is just me. I'm not streaming to impress or show someone anything. This is me. Thank you. And if you're watching, then also thank you. I don't know why you are watching. So yes, as shown in the previous section, given a finite number of bits, a computer can only approximately represent non-integral numbers. Yep, can only approximately represent non-integral numbers. It is often necessary to accept that limitation and perform computations involving approximate values. With due care and diligence, the results will be accurate within some acceptable tolerance. One way to deal with real valued numbers is to simply treat the data as fixed point numbers. Fixed point numbers are treated as integers, but the programmer must keep track of the radix point during each operation. Okay, we will represent fixed point. We will represent a systematic approach to designing fixed point calculations. Okay, fixed point numbers are treated as integers, but the programmer must keep track of the radix point during each operation. That makes sense. So you will treat the set of zeros and ones, the binary, as if they were representing an integer, but then you will also keep track of where the radix point is for that binary number. Okay, the and this representation of numbers is called fixed point numbers. Okay, when using fixed point arithmetic, the programmer needs a convenient way to describe the numbers that are being used. Most languages have standard data types for integers and floating point numbers, but few have support for fixed point numbers. Okay, notable exceptions include PLA1 Ada. Ada was a man, and in whose name we had Ada, the programming language. Now, which provides support for fixed point binary and fixed point decimal numbers. There is also an ISO, International Standard Organization, standard extension to C, which gives some support for fixed point numbers. A few other languages also support fixed point. We will focus on fixed point binary, but the techniques represented can also be applied to fixed point numbers in any base. Using this approach, any language which supports integers can be used to perform fixed point computation. Okay, that is fixed point. But what does floating point number mean? Fixed point numbers uh, use a certain way to represent um, decimal, right? Binary, binimal numbers, that is binary numbers with a radix point. In this approach, the programmer treats the sequence of binary digits as an integer but keeps track of the radix point during every calculation operation. This is one of one of the ways to represent um, fractions. Then what is floating point number? Is it an, another way to represent fractions, or is it just a name for fractional numbers, and fixed point representation is an is a way to represent floating point numbers. Floating point numbers are another way to represent fractions separate from fixed points. Fixed point numbers. Okay. Fixed point numbers versus floating point. Fixed point representation. Binary number is treated as integer, but the programmer keeps track of an implicit radix at a fixed position. For example, if we use 8-bit fixed number with 4 bits for the fraction part, and this format, the binary number, this, which is 26 in decimal, would actually represent 1.625 if interpreted as this. Operations, addition, multiplication, etc. require manually adjusting for the decimal position. Okay, so we would have to shift. Okay. Floating point representation. The position of the radix point is not fixed, but rather encoded within the number itself. Okay, here fixed point. The radix point is fixed. That is the last, in this example, the four MSBs will always represent the integral part of the fraction, and the last four LSBs will always represent the fractional part of the number. That is, the point is fixed. But in floating point representation, the position of the radix point is not fixed but rather encoded within the number itself. Uses a significant or mantissa, an exponent. Okay. It uses a sign bit, a mantissa, and a sign bit, then an exponent, and then a mantissa. Okay, I get it. Yep, when using, yep, here. Interpreting fixed point numbers. How do we interpret them? I hope my stream is not stuck. Nope, it ain't. Interpreting fixed point numbers. Fixed point numbers are stored as integers and integer operations are performed on them. Yep. However, the programmer assigns a radix point location to each number and tracks the radix point through every operation. Each fixed point binary number has three important parameters that describe it. whether the number is signed or unsigned. Okay. The position of the radix point in relation to the right side of the sign bit. In relation to the right side of the sign bit for signed numbers, or the position of the radix in relation to the most significant bit for unsigned numbers. Okay. The representation, the number of fractional bits stored. Okay. Unsigned fixed point numbers will be specified as unsigned U, I, and F. Integer part, fraction part, where I is the position of the radix point in relation to the left side of the most significant bit in relation to the left side of the most significant bit, and F is the number of bits stored in the fractional part. For example, U10 6 indicates that there are 6 bits of precision in the fraction part of the number, and the radix point in its 10 bits to the right or the most significant bit is stored. The layout for this number is shown graphically as this. Okay, so starting from the MSB, 10 bits store the integral part, and then 6 bits store the fractional part, where I is an integer bit and F is a fractional bit. Very small numbers with no integer part may have a negative I. Very small numbers with no integer part may have a negative I. Shit. Like this. So, shit. Okay. For example, this specifies an unsigned number with no integer part. Each 8 leading 0 bits which are not actually stored and 16 bits of fractional precision. The layout for this number is shown graphically as this. Okay, these store the fraction part, and these also store the fraction part there, but there is nothing. That is, we are not storing them. Okay. Likewise, signed fixed point numbers will be specified using the following notation, where I and F are like literally the same thing, whereas I is the position of the radix point in relation to the of the sign bit, right side of the sign bit, and F is the number of fractional bits stored. As with integer 2's complement notation, the sign bit is always leftmost bit, yep, stored. For example, S96 indicates that there are 6 bits in the fractional part of the number, and the radix point is 9 bits to the right of the sign bit. 9 bits to the right of the sign bit. So we are not counting the sign bit itself. We are counting 9 bits to the right of it. And in unsigned bit, instead of 9 there was 10 there, because we were also counting the MSB, which was also storing data about the number, but here we are not using that. It is there to only represent the sign of the number. The layout for this number is shown graphically as this. That makes sense, where I is an integer bit and F is a fractional bit. Very small numbers with no integer parts may have negative I. For example, like this. It specifies a signed number with no integer part, 6 leading sign bits which are not actually stored. A sign bit that is stored, and 15 bits of fraction. Yep, the layout for this number is shown graphically as this. Okay, this stores the sign bit, and this is the fractional part. Okay, this is the fraction part. Okay. Note that the hidden bits in sign number are assumed to be copies of the signed bit, while the hidden bits in an unsigned number are assumed to be zero. Note that the hidden bits in a signed number, wait, yep, my camera is working. Note that the hidden bits in a signed number are assumed to be copies of the signed bit. Okay, while hidden bits in an unsigned number are assumed to be zero. The following figure shows an unsigned fixed point number with 7 bits in the integer part and 9 bits in the fractional part. 7 bits in the integer part and 9 bits in the fractional part. It is 7. This note that the total number of bits is 7 plus 9, 16. So what is this number? This number represents 1. This is 7. 7 plus, what is this? This is 8, 16. 7 plus 16 is 23. 23 point. Oh shit, that is a crazy number. Point. This one represents, what does it represent? Point 0.5, then 0.25, then 0.125, then 0.0625, 0.0625. So I have 0.0625 plus shit 0.00625. Okay, I have 0.625 plus this is 3125 point 0.3125, but I have to skip that. 0.3125 divided by 2 is 0.31015625. Okay, what was it? 15625. 150 plus 0.625. So 0.625 and 0.15625. 15625, it is here, and 0.625 is here. 1 plus 6, 7 plus 1, 5, 5 plus 6 2 7. So I have here 7 7 and then 6 2 5 and 1 5 6 7 8 and 1 6 2 5 5 plus 5 1 6 5 plus 6 7 11. So 1 7 8 1 7 8 1 2 5 for this part, till this part. 7 8 1 2 5 and then god damn it, these two. Okay, 7 8 1 2 5 0 0.078125. And what was this? This was, what the heck was this? This was 16 plus 7, that is 23. That is, yes, 23. 23 plus 0.78125. 0.78125. 0.78125. Here, I have it here. And then I have to divide the 51625 by 4 and add it to the number that I have right now. Okay, I will try to do it. So now the total sum is 0.078125. 0.078125. 0.078125. Okay, I have kept it right there, and now the new thing that I have to add to it, that would be 0.0516, not 516, 15625. 15625 divided by 2. 156 divided by 2 is 0 0 0. 15625 divided by 2 is 0 0 7 6 0 0 7 6 1 2 5. 0 0 7 6 1 2 5. Yep. 0 0 0 0 7 6 1 2 5. Now divide this by 2. 0 0 3 8 7 6 1. 0 0 3 8 3 8 7 6 and 1 2 5. 1 to 5 by 2 is 0 6 to 5. 0 0. Now I have this 0 0 3 8 0625, 0038, 0625, 0038, 0625, and add to it what was the sum before. It was 0.078125. So now I have 00380625. Okay, let me place the digits correctly. 0, 0, and what were the numbers here? 0, 7. So I get 7 at the first place, then like 07 in the answer, and then moving on to the next digit, I had 3 and then 8, and here I have 7 and then 8. So 8 plus 8, 16. So 16 and 1 carry over. So 8, 0, 7, 0, 8, 6, 0, 8, 6, 0, 8, 6. This is the answer that is coming along. 0, 8, 6. What were the numbers? Now I did 3, 8, and then I have 0 there, and then here I have 7, 8, 1. So 1 comes here, and then here I have 8, 0, 8, 6, 1, 0, 8, 6, 1, 8, 6, 1, 8, 6, 1. Okay, I will remember that. 8, 6, 1. And then here I had in the original sum, I had after 1, 2, 5, and 2, 5 plus 6, 2, 5, like 250 plus 6, 2, 5. That would be 6 plus 2, 8, 8, and 5 and 2, 7, 7, 8, 7, and then 5, 8, 7, 5. So the sum right now is 0, 8, 6, 1, 0, 0, 8, 6, 1, 8, 6, 1, 8, 6, 1, 8, 6, 1, and then what was the later part? 8, 7, 5. 0, 8, 6, 1, 8, 7, 5. That is a big number. Okay. 0, 8, 6, 1, 8, 6, 1, 8, 7, 5. I have to add to it the value for this last fractional digit, which would be the half of what was the last number that I added. Okay. 0, 8, 6, 1. I have to repeat it a few times so that I can remember it when I add to it the next time. 0, 8, 6, 1, 8, 6, 1, 8, 7, 5. 0, 8, 6, 1, 8, 7, 5. 0, 8, 6, 1, 8, 7, 5. Okay, I will keep it here. And now the new sum. New sum would be the new number that I have to add would be half of what I added earlier. And what was the some number that I added earlier? That was 0, 0, 3, 8, 00380 625. I have to have this 0038 0019 0019 03125 001903125 0039 Now add to it the original sum, the sum running sum should be now. I have two zeros in the front. How many digits do I have in the sum? I have 0, 6, 1, 8, a 0, 8, 6, 1, 0, 8, 6, 1, 8, 7, 5, 7, 7, 7, 7 digits. Okay, I have to only care about 7 digits from this sum, and I can simply drag the last seven. What are the 7 digits from the sum right now? 001903 1. Okay, so for 00 plus 08, I get 808, and 19 plus 0861. 61 plus 19. That is 80. 80. So, okay. 0880 plus 0 from the new sum. 00. 0880 plus 0 from here, and from the sum, and 8 861 861 875. 8 plus 0 8, so 0 880 8 0 880 8, okay, and then 0 8 8 0 8. Okay, now only two digits are remaining. 08802 0880 then from the new sum I have, after 190, then I have 3 and 1, so 3 1 plus, from here I had 8 6 1 8, no, not 861, 8 7 5 7 5 plus 3 1. Shit, I will have a carry over. Okay, 7 5 is 7 5 plus 3 1. Yep, 3 1 3 1. 7 5 plus 3 1. 3 1 plus 7 5, that is 106. So 0 0. That 8 becomes 9. So 0. Now this is the final answer. What was that? 23.088809 and 0 0 and 3125. And I hope that this is correct. It would be funny if it is not, but okay. Let's see. Let's see. Okay, it was a long shot, but you got, I guess, pretty good. I don't know. This was pretty good. Let's see where we went wrong. 088. Huh? 2323 is of course correct. And then, okay, did I add a bit more than I should? Nope. Nope. I didn't. Let's see. 1 divided by 16. That is 0.625. That is the first number that I added. Then 1 divided by 64. That is 0.1565. And I guess that I added it correctly. Then I have 1 divided by 256.39065. Was this the number? 000? No, I took it as 38. Why did I do that? 128 is 78125. Hmm. Okay, my calculation was wrong at some point. But yeah, pretty good, pretty good, pretty good, pretty close, I would say. Likewise, the following, well, this is called cognitive mapping, I guess. And I suppose this is how Magnus Carlsen can play blindfolded with multiple people at the same time. That is just crazy. Crazy level mind mapping. Now, likewise, the following figure shows a signed fixed point number with 9 bits in the integer part and 6 bits in the fraction part. It is 96 number. Note the following total number. Okay, can we do this? Okay, we can calculate this much fraction part. This is little. Okay, zero point 0.5 plus 0.256. Okay, I took it. No, that was good. Point 500, 500 plus 125, that is 625. 625 plus 125 divided by 2, 0.0625. That again divided by 2, 0.031, 312625, 3125, 3125. Okay, 3125 plus 03125 plus 625031, 31 plus 25, that is 515656. So I have 656 65625, 65625. That is the running thing. 65625, 65625. Okay, that is the sum right now. And then I have 03125 divided by 2, 015312516. So 15625, 0152625, 15625 plus, what was the sum before? The sum before was 0.65625. 6 plus 006, and then 6 5, and I have here 15615 plus 56, 1 5 plus 5 6 is 6671, 71. So 671, and here I have 3 1, no, 15625. So I have 671. That is going to be the final answer, around the final answer. Point 671 plus, then after it I had 681. What the fuck? Zero. What was the running total? Zero. Yes, 6.0656. I've done till that, and then 25, right? 25. Now I have to add 25 to the other digits in the new number that I have to add. This was 0.1501556. I have done till that. Then 156, 25 plus 5, 6, 7, 1, 5. This might also be wrong. 671, 875, 671. Ah. So I have a zero point 0.5 plus 125, right? 1 divided by 8 is 125. Yep. And then I added, what did I add? 0.3125. Yep, I added 3125. And then what did I add? I add 0.015625. 15625. So yeah, there must have been some mistake in adding and subtracting, and adding only. There is no subtraction here. Shit, that was a crazy experience. Now, note that in the above two examples, the patterns of bits are identical. The value of a number depends upon how it is interpreted. The notation that we have introduced allows us to easily specify exactly how a number is to be interpreted. For example, signed values. If the first bit is non-zero, then the two's complement should be taken before the number is evaluated. For the following number, this signed number has a negative value. This. So to evaluate this, the value of this number in base 10 can be computed by taking the two's complement, summing the values of the non-zero bits, and adding a negative sign to the result. That makes sense. The two's complement of this is this. Yep, the value of this number is this. For a final example, we will interpret this bit pattern as signed minus 516 in that format that is laid out here. Okay, here. So this is signed. So I have to take one's two's complement of this number. That will give me this. Okay, that will give me this. The value of this number is in base 10 can be computed by taking two's complement, summing the values of the non-zero bits and adding a negative sign to the result. The two's complement is this. Yep. And the value of this number is interpreted as this. Yep, like that. And this is the number. And this would be really fucking hard to calculate in mind. But maybe that is just me putting limitations on my brain. Yep, yep, yep. That is crazy number to calculate in mind. I couldn't even get this one, this is small number correct. Ah, but okay, over time I will improve. Q notation. Fixed point number formats can also be represented using Q notation, which was developed by Texas Instruments. Texas Instruments is a good company, legendary in some sorts. They made the bipolar transistor very famous and cheaply available for microprocessor building. Q notation is equivalent to the SU format used in this book, except that the integer portion is not always fully specified. In general, Q formats are specified as QMN, where M is the number of integer bits and N is the number of fractional bits. If a fixed word size W is being used by M, then M may be omitted and assumed to be W minus N. For example, uh, Q10 number has 10 fractional bits and the number of integer bits is not specified but is assumed to be the number of bits required to complete a word of data. 2 4 number has this represents number in using 6 bits. Number has 2 integer and 4 fraction bits in 6-bit word. There are two conflicting conventions for dealing with sign, sign bits. One convention, the sign bit is included as part of M, and in other it is not. When using Q notation, it is important to state which convention is being used. Additionally, U may be prefixed to indicate an unsigned value. For example, this is equivalent to U, this and this is equivalent to this. Okay, properties of fixed point numbers. Once the decision has been made to use fixed point calculations, the programmer must make some decisions about the specific representation of each fixed point variable. The combination of size and radix will affect several properties of the number, including precision, resolution, accuracy, range, or dynamic range. Okay, precision, how truly accurate, how high precision means less deviation from the actual number. The maximum number of non-zero bits representable. Okay, the maximum number of raw non-zero bits representable, because in some representation we are using these non-existent bits, but they are zero. We cannot treat them as one. Right. Resolution, the smallest non-zero magnitude representable. Okay. Accuracy, the magnitude of the maximum difference between a true real value and its approximate representation. The magnitude of maximum difference. That. Okay. Range, the difference between the largest and the smallest number that can be represented. And dynamic range, the ratio of the maximum absolute value and the minimum absolute value representable. Maximum absolute value and minimum absolute value. Minimum absolute value, I guess, would be zero, and the maximum absolute value would be either positive or negative, but it's only absolute value, not with sign. Given a number is specified using the notation introduced previously, we can determine its properties. For example, an S96 number has the following properties. Yep, it has 16 bits, and resolution, the smallest digit that can be represented as this. Yep, non-zero to the smallest. And accuracy is resolution divided by 2. Magnitude of the maximum difference between a true value and its approximate representation. Between a true value and its approximate representation. Magnitude of maximum difference between a true value and its approximate representation. Okay, that makes some sense. Now, range minimum value is this. Oh, minus and then that. Maximum value is this. All bits are 1 except the sign bit. And range is this plus this, that is subtracting this, and this is the range. Oh, and dynamic range for assigned bit point rational representation signed I and F. The dynamic range is this 2 into 2 power I divided by 2 power minus F equals 2 plus. Therefore, the dynamic range of this is 65536. Okay. Hmm. Okay, that makes some sense, I guess. Fixed point operations we have next. Now, being aware of these properties, the programmer can select fixed point representations that fit the task that they are trying to solve. This allows the programmer to strive for very efficient code by using the smallest fixed point representation possible, while it still guarantees that the results of computations will be within some limits of error tolerance. Okay, fixed point operations. And how long has this been? Only 43 minutes. That is crazy. Yep, stream number 21 for the assembly language series. Now, fixed point numbers are actually stored as integers, and all of the integer mathematical operations can be used. However, some care must be taken to track the radix point at each stage of the computation. The advantage of fixed point calculations are that the operations are very fast and can be performed on any computer, even if it does not have the special hardware supported for non-integral numbers. Fixed point addition and subtraction. Fixed point addition and subtraction work exactly like their integer counterparts. Okay, point one gives some example of fixed point addition with signed numbers. Okay, note that in each case the numbers are aligned so that they have the same number of bits in their fractional part. The numbers are aligned so that they have same number of bits in their fractional part. That makes sense. Here. Uh, yep. This requirement is the only difference between integer and fixed point addition. In fact, integer arithmetic is just fixed point arithmetic with no bits in the fractional part. The arithmetic that was covered in chapter 7 was fixed point arithmetic only with high and number of fractional bits are zero numbers. In other words, integers and natural numbers can be considered as fixed point numbers where the number of fractional bits f is zero. Note, we are simply extending our knowledge with numbers where f is not equal to 0, that is, we have some fractional bits. There are some rules which must be followed to ensure that the results are correct. The rules for subtraction are the same as the rules for addition. Since we are using 2's complement mathematics, subtraction is performed using addition. Okay, that makes sense. Suppose we want to add this 2 and this in number. The radix point are different, so we can left shift this by 4, but we would lose our MSBs, or we can right shift this one by 4. The radix points are different locations, so we cannot simply add them. Instead, we must shift one of the numbers, changing its format until radix points are aligned. The choice of which one to shift on what format we desire for the result. We desire 8 bits of fraction in our result. Then we would shift this left by 4 bits, converting it into 7, 8. We did not lose any data. That is also crazy. With the radix point aligned, we simply use an integer addition operation to add the two numbers. The result will have its radix point in the same location as the two numbers being added. Fixed point multiplication. Align them and then just multiply, it seems. Recall that the result of multiplying n bits by m bits is an n plus m bit number. In case of fixed point numbers, the size of the fractional part of the result is the same as the sum of the number of fractional bits of each. So 2 plus 1, I should have 3. I do have goddamn 3 numbers. Okay, fractional bits each number, and the total size of the result is the sum of the total number of bits in each number. 1, 2, 3, 4, 1, 2, 3, 7, 1, 2, 3, 1, 2, 3, 7. Yeah. Consider the following example where two unsigned 53 numbers are multiplied together. The result is 6, 6, and 10. 10. The number of bits in the result is the same as the sum of the number of bits of the multiplicand and the multiplier. The number of fractional bits in the result is the sum of the number of fractional bits in the multiplicand and the multiplier. There are three simple rules to predict the resulting format when multiplying any two fixed point numbers. Okay, listing 7 point shit. Now after like 10 to 20 pages, we have some assembly code. That is crazy. This book is now becoming more maths and less assembly. Like I said, listing 8.1 examples of fixed point multiplication in assembly, arch assembly, and here we have this x is a into b and this 10 10 o. I have 10, 5, 10, 5, 10. Multiply the two numbers. This. Produce this. I multiply two numbers, W1 and W2. Sign, multiply long, and save the result in the 0th register, and then I arithmetic right shift the value by 5 times. Multiply 2 unsigned number. Multiply two unsigned 12 six numbers and produce this result. Signed, unsigned to multiply the contents of fourth and fifth register and save it into the third. That is A into B gives me this number, that is 12 plus 22, that is 24 bits. Oh, oh, 12 plus 4. Okay, 4 plus 4 is 8 and 12 plus 12 is 22, but I want to lose the two MSBs, therefore I left shift, logically shift right the value. And the same thing is happening here and then here. Okay, now, unsigned multiplication, the result of multiplying two unsigned integers numbers, this and this is I plus I1 plus I2 and F1 plus F2, and same goes for unsigned, and here also goes the same. The result of multiplying two signed numbers is I1 plus I2 plus 1 for the sign bit, I suppose. Note that this rule works for integers as well as fixed point numbers. Since integers are really fixed point numbers with f equals 0, the programmer desires a particular format for the result, then the multiply is followed by an appropriate shift. Okay, that makes sense. Now, listing 8.1 gives some examples for fixed point multiplication using the ARM multiply instructions. In each case, the result is shifted to produce the desired format. It is the responsibility of the programmer to know what type of fixed point number is produced after each multiplication and to adjust the result by shifting if necessary. I do not fully understand what the heck is going on here. Like, why are they being multiplied and then shifted? Let's see, ask ChatGPT. Um, these are assembly instructions, like like ChatGPT doesn't know already. Assembly instructions in AArch64. How can I? These are assembly instructions in AArch64. They are multiplying two fixed point numbers which are stored in W1 and W2 and storing the result in X0 and then right shifting the result. 510, 510. When I multiply this and this, I get the result that I get is this 21 and 10. Therefore, to lose the 5 LSBs, therefore I right shift this by 5. That makes sense. And here I get 8 because 4 plus 4 is 8. Therefore, I right shift this by 2 to lose the 2 LSBs. That also makes goddamn sense. Multiply to this numbers and produce a 15 bit. I will right shift by 15. That makes sense. And this I will right shift by arithmetic right shift because this is sign multiply and this is unsigned. Therefore, logical shift right. That also makes sense. Okay, so I do understand. I do understand this. Fixed point division. The rule for determining the format of the result of division is more complicated than one For multiplication, we will first consider only unsigned division for a dividend with format this by divisor with format this. We will first consider only unsigned division of a dividend with format this and divisor with format this. Results of fixed point division. Consider the results of dividing two fixed point numbers using integer operations with limited precision. The value of the least significant bits of the dividend n is the value of the least significant bit of the dividend n is 2 power n. Dividend dividend is the number that I want to divide. The value of the least significant bit of the dividend n is 2 into fi, and f and I are f and I. Okay, and the value of the least significant bit of the divisor is, oh, not fi but f1. Okay, that makes sense. That makes sense. I have f1 digits and f1 digits to the right of the radix point is equivalent to f power minus 1, and same for the divisor, which has f2 digits. In order to perform the division using integer operations, it is necessary to multiply n by 2 power f and multiply d by 2 power n by 2 power f2, so that the number does become an integer. So the both numbers are integers, therefore the division operation can be written as this. Okay, n divided by d is this n divided by d multiplied by 2 power f1 minus f2. Note that no multiplication is actually performed. Instead, the programmer mentally shifts the radix point of the divisor and dividend, then computes the radix point of the result. For example, given two numbers which are this, the division operation is accomplished by converting them both to integers, performing the division, then computing the location of the radix point. Convert this and this. Divide the dividend by the divisor, and this becomes 0. Note that the result is an integer. If the programmer, okay, so this gives me the power of the radix point, it seems. Yeah. The value that remains here is tells me how many digits after the radix point are there. I feel like sometimes the stream is stopping, but it is not. Es funktioniert nicht. Es ist gut. Ich kann ein bisschen Deutsch sprechen, aber mein Deutsch ist nicht so viel gut. Note that the result is an integer. If the programmer wants to have some fractional bits in the result, then the dividend must be shifted to the left before the division is performed. If the programmer wants to have some fractional bits in the result, then the dividend must be shifted to the left before the division is performed. Okay. If the programmer wants to have FQ fractional bits in the quotient, then the amount that the dividend must be shifted can be easily computed as this. Okay, the wants to have F fraction bits in the quotient, then the amount that must be shifted can be easily computed as this. This much is how many fractional bits I want in the result, and this one is how many fractional bits there actually are. Why am I adding them? For example, suppose that the programmer wants to divide this stored as 28.3 by this, which is also stored as 28.3, 3, and which is to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits in the result. The programmer would, 28.3, 3, and wishes to have 6 fractional bits This minus this would give me the actual number of fractional bits present, right? Yep. Yeah, since here this in this I know that f1 minus f2 should be negative. Therefore, I will shift the numerator, that is the dividend, by whatever this thing says, which would be equivalent to n multiplied by this and divided by this. And if I want some more fractional bits, then I can add it to the shift. For example, the programmer wants to divide this and this by this. The programmer would shift this number left to by 6 bits, then perform the division and compute the position of the radix in the result as shown. Compute the position of the radix. Don't I have the position of the radix because of this? That is equal to the amount of shift that I did. And in this, we do 6 shifts. Did I do six shifts? 0, 1, 1. I should have 0, 1, 1, and then 6 zeros. 1, 2, 3, 5, 6. Yep, I have 6 zeros, and this I do, and then multiply it by this. I got to meet. Wait, multiply this minus this. Okay, since this will give me an integer, I have to keep this here to tell me the radix point, which is equal to the amount of shift that I did, so that I can unshift it afterwards. Since the divisor may be between 0 and 1, yes, maybe between 0 and 1, the quotient may actually require more integer bits than there are in the dividend. Yes, makes sense. Consider the largest possible value of the dividend, that is n max is 2 power I, that would give me the maximum number, and minus the fraction part, and the smallest positive number for the divisor would be this. Yep. Sorry, me sleepy. And why am I subtracting this? Should I not just add it? N max. Okay. But why am I subtracting this? Should I not just add it? Because that is how the things are calculated. Maybe this is a special way. Nope. I am working with unsigned bits, so this is not a special way. In unsigned bit, the maximum amount is, yeah, yeah, I guess this works. Yeah, I guess this works because instead of putting one at every place and then calculating those ones and adding them together, I am taking one for the bit that is left to the MSB and subtracting from that the fractional part. A fractional parts LSB. Yes, that I guess makes sense. And the smallest positive value for the divisor can be this. There, for the maximum quotient can be given by this. Which one is this? Numerator divided by denominator, and then I get this minus this. Taking the limit of the previous equation, f1 minus f2, reaching minus infinity. That is, f1 is so far beyond f2 that I'm reaching minus infinity. Then q maximum quotient is equal to the integral part of the dividend plus the fraction part of the divisor. Okay, provides the following bound on how many bits are required in the integer part of the quotient. This Qmax is at least 2i plus f2 number of bits. Okay, I'm getting an idea of what is happening. We are dividing and treating these numbers as integers, even though they are fractions. That is the whole concept of fixed point numbers. Therefore, the first case, the quotient will require I1 plus F2 integer bits. For example, if we divide U35 equals this by this, a very small number equals this, we end up with this equals this. Okay, which does not take more number of bits than the dividend. I guess which was the whole, which goes opposite to the whole point of which you were saying here. The same thought process can be used to determine the results of signed division as well. Mixed division between signed and unsigned numbers. The result can be reduced to the following three rules. Maintaining precision. But damn it, this is like very maths and very not assembly. Yep, the stream is going to camera and the screen is also working. Mm. Now, consider the results when you unsigned number or wait unsigned division, the results of dividing an unsigned fixed point number this by an unsigned number, this is this number. The number of fractional bits is I1 minus I2 and number of integral bits is I1 plus F2. Okay, these things are, I am unable to understand what is going on currently. Like, I do not fully grasp this all, but that is the thing. I have at least some idea with which I can move forward, and when I read this again in some other book, I will be better equipped to understand this. Mixed division, the result of dividing two fixed point numbers where one of them is signed and the other is unsigned. As this, then this is the representation. I will get a signed number as the quotient. Signed division when both the numbers are fixed point numbers signed. This I1 plus F2 plus 1 and F1 minus F2 number. Oh, consider the results when a U23 unsigned 23A equals this 3 and 3 1 2 3 equals this is divided by 4 1 which has one decimal place equals 8. The quotient is this. Shit. 8 divided by this is very small number which requires 6 bits in the fractional part. However, if we perform the division, then according to the rules shown above, the result will be -2. This indicates that the result would have to be shifted 2 bits to the left to restore it to an integer, and the result is only accurate within plus minus 4. Plus minus 4, that is an integer. When f2 greater than f1, that is the number of fraction bytes in the divisor is greater than the number of fractional bytes in the dividend. Blindly applying the rules will sometimes result in a negative fractional part. To avoid this, how can you have a negative fractional part? To avoid this, the dividend can be shifted left so that it has at least as many fractional bits as the divisor. Yes, that makes sense. This leads to the following rule. If f2 greater than f1, then convert the divisor to s1 x where x greater than f2. Convert the divisor into this. Okay. Then apply the appropriate rule. So I will just increase it even further. This is the divisor. Ooh. Then apply the appropriate rules. For example, dividing 52 by u3. Oh god damn it. Should result in n7 minus 10, but shifting the 5 to 16 bits to the left will assume in n 518, and dividing that by f12 will result in 17.6. Okay. Maintaining precision, maintaining precision. Recall that integer division produces a result and a remainder. In order to maintain precision, it is necessary to perform the integer division operation in such a way that all the significant bits are in the result and only insignificant bits are left in the remainder. Yes, the easiest way to accomplish this is by shifting the dividend to the left before the division is performed. To find a rule which determines the shift necessary to maintain full precision in the quotient, consider the worst case. The maximum valid value of dividend is n minimum, which is 2 power minus f1. And the largest value for the divisor can be I2 f1 minus I2 minus 2 power minus f2. That makes sense, and this is the way we used before. Yep. And therefore, the minimum positive quotient is given by this. Minimum positive quotient. Okay. Therefore, in the worst case, the quotient will require I2 plus F1 fractional bits to maintain precision. However, fewer bits can be reserved if full precision is not required. That also makes sense. Recall that the least significant bit of the will be quotient will be minus I I2 plus F1. And then shifting the dividend left by I1 plus F2 bits will convert it into this. Okay, what is happening with all of this? I am reading all of this to understand binary division, right? How does how is binary division performed? But is that my main purpose with this book? With this book, my main purpose is to understand assembly language, which I do to really more extent than I understood before starting with this. And understanding binary multiplication and division and other stuff about how floating point and everything is represented in binary, that was not my main goal with this stream. And I am streaming this so that I have responsibility on myself so that I continue. And it would have been really hard to get this far, like more than halfway through the book, if I was not streaming all of this. And this I am streaming not to show anybody what I am studying. Well, yes, to some extent, I can maybe send this to some recruiters maybe in the future at some point. But the main goal is for me to not waste my time and actually learn and have something pushing me forward. But right now, I am getting the feeling that the reason that I am continuing this, even after having understanding about assembly, as much understanding as I wanted when I started this, I am continuing this because I now have a sort of social pressure. I feel like people are watching me, and thus I cannot leave this in middle. but that goes against the fact that I do not want to waste my time. And I have to take decisions on my own. I cannot waste my time continuing this stream for like 5 to 10 more streams, even if I have understood assembly as much as I wanted to, as much as I had in mind. And I will, if I ever need assembly more than what I have already studied, then I can always come back to it, come back to this book. But right now, I have more than sufficient understanding of assembly that I am ever, not ever, but going to need for now, right? And so now we are going to not skip, but skim. I know that, and the main reason that I am skipping all of this binary stuff is because I have this book, Hacker's Delight, which is just about binary and stuff. Everything that is related to binary. Let me see the content it has. First of all, it has basics, then it has powers of two, boundaries, then it has counting bits, arithmetic bounds, searching words. Searching words was a program in C language. And uh, rearranging bits and bytes, multiplication, integer division by constants, which was something in here, and this book has 70 pages on just integer division by constants. And then I have some elementary functions. Okay. Then usual based for number system, unusual basis for number system, my bad. And then gray code, cyclic redundancy check, error checking codes, Hilbert's curve, floating point, formulas for primes. Yeah, this is a good book. And this is the reason that I am willing to stop this series. Well, like not I have not decided to stop this, but I have to only continue this if there is value in pursuing this. I cannot blindly go after this just because I started this. I will only continue this if I see value, and I can easily continue, give this book my time and understand every single thing which I might and might not need in the future. But the thing is, I feel like fixed point input and output. Thing is, I feel like I know quite a bit about assembly from this book, and this can very well be my last stream, but I have not completed my 2 hours mark. So what do? We're going to skim through the remaining chapters. This one is non-integral mathematics. We have formats and constants for factorial terms. Factorial shit. Okay, and what do we have? Putting it all together in some way. And then a big ass assembly program. Yep, it is 228 lines long. This performance comparison. Yet all of this defeats the purpose. My main purpose with this book was to learn assembly, and I do not have to feel bad if I leave this book from here. Because why? Because the thing is that these streams are not are for me. These streams are for me, and if I do not see the purpose in continuing something, then I will stop continuing this. But this could also be me making excuses. But it is not that I am stopping this stream and then I will not do anything. I have this book for binary and I will be reading this, but I will not be streaming this, of course, because this is a physical book and this is a beautiful book and I do not want to read it from PDF because I have the physical copy. Yeah, the thing is this, I feel like this might be the last stream for assembly language, and I have understood assembly language, the assembly part, to a good extent. to a I have come pretty far in my understanding in assembly. Introduction, GNU assembly syntax, load, store, branch instructions, data processing, and other instructions. And after this, I can focus more on my C streams and maybe increase the number of C streams that I do to twice a day instead of only once. And after completing my C streams, the C programming language streams, I will try to make a compiler or transpiler in the C language so that I have an understanding about how languages work. But before doing that, I saw a video by the Primogen how to learn a language. He said that first you can do 5 to 10 advent of code problems and then do make a WebSocket server so that you can people can add and leave rooms and chat with people. Okay, I will do that. I do not have any idea how that is done, but I will do that. And then make a transpiler in that language that you want to learn. So transpiler, making a transpiler is going to be the third step. And the first step, wait, Skeleton, the Skeleton. I have the picture in my mind, but you guys cannot see it. So learning a language, learn N N I N G learning C. For that, first, well, what I'm doing right now, reading the book, reading uh, R and K. R and K is Ritchie and Kernighan, the writers of the book. And then after reading the book, we'll do advent of code. About let's say 10 to 12 questions as far as I can go without my lack of DSA skills becoming apparent. And then after advent of code, we will be making a web socket socket server that will allow people to server that will allow people to join and leave rooms. This will be terminal based. I will make a front end for it also. Terminal based. And this is going to be pretty hard because I have no idea how I will do that. Yeah, and this is all going to be terminal based, so this is going to be pretty hard, but okay, we will do it. And then a transpiler, which converts code from one language to another. For example, the Babel transpiler, which converts code from the latest JavaScript standard, ES standard, ECMAScript standard to some previous standard so that old browsers are also compatible with that code. So, yeah, I don't know how tough building a transpiler is going to be because I have never built it, but I know a few stages. That is, first I have to get a parser. A parser will give me an abstract syntax tree, tokens, something, and then I change that abstract syntax tree from one language to another, and then that abstract syntax tree AST is converted into the code for that language. Hmm. So yeah, for assembly, assembly, we have done pretty good. We came from zero to, well, not 100, but pretty far. Good, from zero to good, and I have enough knowledge about the assembly language that I need. And if I ever want to understand anything, I can just look it up. Well, at least I have understood the basics. Well, assembly is basic. Understood the basics of how assembly language works and how processors work and things happen in the CPU, memory management, and other stuff. And if I continue more into that route, because it would be really hard because I do not want to continue and I do not have to continue. And it would be really hard to find motivation because I do not think that continuing in this route is going to benefit me. Will only take up my time, and in the end, I will be only a little better at assembly, right? The things that I learn in assembly from now on are going to be harder to learn. First of all, because I do not want to learn them anymore, and second, because topics will become more complex, right? Abstract in non-integer mathematics, floating point. We can do this part. We can do this part. Advanced SIMD instructions. This is more assembly and running without an output. Okay, we can skip all of this mathematics portion and we can start from here. Start from here and go till the end. Huh, that would be good. Yeah, 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 yeah. That is good. That is good. Okay, so we this is not going to be the last stream. We got this advanced SIMD instructions, which is assembly, not anything else. Floating point. We were at non-integral mathematics fixed point, and now we are skipping that and then floating point, and we are coming on to advanced SIMD. That is single instruction, multiple data instructions, and devices. How I can access devices and then running without an operating system. This is going to be cool, and I want to learn them. So that is cool. And I will also benefit from learning these things. And yeah, that is it. That is my gut feeling that I will benefit. And what is the time? 1 hour 27 minutes. That is also fine. So we can start learning now. I can we can start learning this now. Chapter number 10. What 350? A little above 350. Quite a bit above. Hmm. That is landscape. Advanced SIMD instructions. Okay. In addition to FP and neon instructions described in the previous chapter, FP and neon instructions. What are F, FP and neon instructions in AArch64? Ah, shit! It went all the way down. That is cool. R64, 64-bit ARM architecture, FP floating point instructions, and Neon advanced SIMD instructions are a part of the floating point and vector processing extensions. These instructions operate on floating point and SIMD registers. V registers provide efficient computation for mathematical and multimedia tasks. FP point instructions. I do not understand this, but let's move on to this. More detail. FP instructions operate on floating point numbers. Okay, that makes sense. Single or double precision and include basic arithmetic comparisons, conversions, and special operations. Basic arithmetic comparisons, conversions, and special operations. Floating point registers uses okay V0 to V30 shared with neon. Each register can okay. So I guess we have to backtrack. Yep, new instructions mentioned. Yep, there were new instructions in this chapter. We cannot skip them. We have to understand them. Yo, Technoblade never dies. Floating point. Okay. And see, see, this chapter is mostly mathematics. But let's see what was here. We were on this chapter, right? Yep. Computing sine and cosine. Yep, we were on this chapter. It tells us a way to compute sine and cosine, then format for powers of 2. Okay, we can skip all this mathematics and putting it all together. We just saw that a minute ago. Now this is backtracking and we are coming back to what we lost. Floating point numbers. Okay, half precision. It takes, yep. So the thing is here, half precision is a way to describe floating point numbers, is a way to describe fraction numbers. What is 8.7? 8.7 is floating point numbers. Okay. Half precision is a way to represent floating point numbers where we use 16 bits and the first bit is used to represent the sign of the number, and the next how many, 5 bits are used to store the exponent, and then the last 9 bits are used to store the mantissa. The mantissa the significant aka mantissa or fractional part is stored using a sign magnitude coding with uh, bit 15, with the bit 15 being the sign bit. Okay, how is mantissa calculated? Mantissa is the numbers, right? Numbers. The 9 MSBs for the binary number. Uh, we have single precision, which uses 32 bits, and then we have double precision, which uses 64 bits. Quad precision, which uses 128 bits. Then floating point operations. Now, are there any new instructions for floating point operation? Nope. Ethics case study. Patriot missile failure due to some floating point number error, I suppose. Then chapter summary, and then we are done with this chapter. Okay, and now floating point. For ARM v7 and previous architectures, floating point is provided by an optional vector float pointer coprocessor, a different processor. Okay, many ARM v7 processors also support the Neon extension. All AArch64 processors support a version of Neon referring to advanced SIMD. For brevity, this book will often use the term Neon to refer to advanced SIMD. Advanced SIMD supports not only floating point but also integers and fixed point numbers. Integers and fixed point numbers. The remainder of this chapter will cover the floating point operations that are inherited from or similar to the instructions provided by the old VFP coprocessor. Vector floating point. Vector floating point coprocessor. Okay, an overview of what the heck is happening here. Okay. Yep, I stopped streaming on Twitch. Now an overview. Historically, ARM has implemented floating point operations by adding a coprocessor to the CPU. The coprocessor extends the instruction set that is supported by the system. There are 5 major revisions of the ARM floating point instruction set and coprocessor. Vector floating point version 1. Vector floating point coprocessor version 1 is obsolete. What is obsolete? No longer produced or out of date. Okay. Version 2, an optional extension to the ARM V5 and V7 processors. VF2 has 64-bit floating point U. What is FPU? Somewhere here. Nope. Floating point unsigned registers, I suppose. Uh, Vector floating point version 3, an optional extension to V7 processors. It is backward compatible with VF2 except it cannot trap floating point exceptions. VF3 D32 has 32 and 64-bit FPU registers. Some processors have V3 D16 which supports only 64. Has 32. D32 has 32 64-bit FPUs registers. Some processors have VF3 D16 which support only 16 64-bit processors. V3 adds several new instructions to the VF instruction set. VFP, vector floating point. Okay, VFP version 4 implemented on Core Cortex ARM V7 processor. VF version 4 has 32 64-bit FPU registers. It adds both half precision extension and multiply accumulate instructions to the features. Some processors have D16 which support 16 64-bit FPU registers, and then Neon. Neon defines single instruction multiple data extensions to the instruction set. Neon supports floating point instruction set floating point instruction set along with integer operations. The Neon instruction set allows for a single instruction to perform multiple operations on multiple pieces of data. Okay. AArch64 integrates floating point and single instruction multiple data more tightly into the processor core while still maintaining instructions that are similar to the original FP Neon. Okay. And SIMD mode. Okay. Now we have this V0 to V31 something. These were the registers that we have been working till now. AArch64 integer left and FP and Neon right. User program register. UPR. Figure 9.1 shows the 32 AArch64 integer registers and the additional registers provided by the AArch64 advanced SIMD instruction set as shown in figure 9.2. This AArch64 FP Neon instructions provide the ability to view the register set as 32 quadruple word 128-bit registers. Okay, these are 128-bit registers and there are 32 of them named through Q0 through Q1, Q for quadruple, and we generally use R or X or W. Okay, and we can also use V to refer to them. Floating point CR, floating point stack register. I don't know. Named through Q0 through Q1 or 31, Q31 or 32 double word 64-bit registers named through D0 through D31. Okay, if you want to use the full 128-bit version of the register, then we write Q for quadruple. And if we only want to use 64-bit registers, then you write D for digit double as 32 single word registers named. We can also use 32-bit by using S0 through S31. Each register can also be referred as a half-word register H0 through H31 or a byte register B0 through B31. Additionally, pointers of each registers can be referred to by using a subscript notation such as V1 S64 1, which refers to the upper 64 bits of register V1. register V1 and pointf 64 1 upper 64 bits, one like start from above. I guess the processor supports IEEE single precision, double precision numbers. So what I want to understand is floating point arithmetic. Uh, okay, so what exactly are these FP and neon? Are they standards where registers are defined and an instruction set is defined to handle operations related to floating point, and then hardware is is made by the processor manufacturer according to this standard. Is it just another instruction set architecture? What exactly are, yes, FP floating point and Neon advanced SIMD are extensions of the AArch64 V8A instruction set architecture. They are not separate ISAs but part of the ARM64, especially designed for floating point and vector processing. Floating point FP is the floating point extension in ARch64 implementing IEEE 754 floating point arithmetic, the standard for floating point computers. It defines registers V0 through V31 with the scalar floating point operations, instructions, addition, subtraction, multiplication, division, comparison, conversions, etc. Hardware support. ARM processors implement floating point execution units to process these instructions. Think of FP as a specification within the ARM64 for floating point arithmetic. Neon advanced SIMD. Neon is ARM's vector processing SIMD. Vector processing. What is vector processing SIMD? Is designed for parallel computation. Example, multimedia signal processing, cryptography. It defines registers V0 through V31 treats treats as 128-bit SIMD registers, Q registers. Instructions full multiply. Hardware support. Neon requires a dedicated SIMD execution unit in the CPU. Hardware support. Implement floating point execution units to process these instructions. Implement floating point execution units. Think of Neon as ARM's built-in vector processing unit, similar to x86 SSE and AVX. ARM Are these just another ISA? No, FP and Neon are not separate ISAs. They are extension to the ARM ISA, ARch64. ARM defines the ISA including FP and Neon. ARM, the company Advanced Risk Machines, develops the ISA specification that includes general purpose, floating point, and SIMD instructions. Okay, processor manufacturers implement the hardware. Companies like Apple, Qualcomm, and Broadcom design CPUs. Example, Apple's M1, Qualcomm's Snapdragon. Qualcomm is the company that makes Snapdragon. Okay, semiconductor company. Where is it located? Nasdaq. Uh, President founded California, San Diego. What news images? Like what is their logo or something? Okay, they Qualcomm. They make Snapdragon chips for processors processors for phones. Okay, Qualcomm. And ARM processor manufacturers, company like this, make their own ARMs. ISA software uses these instructions compiler example GCC, Clang, generate FP and Neon instructions when optimizing for code. So FP and Neon are standardized instruction sets within the ARM architecture, and CPU manufacturers implement these extensions as part of their ARM-based processors. So there is a main processor which has registers for general purpose, and this is used for all the general purpose instruction execution. And then there are processors uh, for the specifications. Is that it? Like, and and these multiple processors are either on a single chip chip uh, microprocessor or on multiple. Let's see what is. Yes, you are getting the right idea. Let's break it down in terms of how general purpose processing and special purpose processing work with ARM64 based microprocessor. The main processor, general purpose processor. This is the core CPU which executes general purpose integer instructions, addition, subtraction, branching, memory operation, etc. Uses general purpose registers, GRPs, registers 0 to through 30, stack pointer, program counter. This is where normal program execution happens. Specialized processing units. In addition to the main processor, ARM CPUs often include specialized execution units for different tasks. These may be on the same chip, most common in modern ARM designs, separate coprocessors, less common in newer ARM chips, but historically used. A floating point unit, FPU, executes floating point operations, uses V0 to V33, which holds single double quad precision values instructions. These and modern ARM processors integrate the FPU directly into the core CPU. Okay, Neon SIMD unit, hardware vector processing SIMD for parallel computations, uses the same registers but treats them as 128-bit wide vectors. Okay, instructions. These adds 432-bit numbers in parallel. Also integrates into the core in modern ARM design. Other is specialized units optional. Cryptographic engineers, machine learning accelerators, Apple's neural engine in M1, and digital signal processing units for audio video processing. Are these separate processors? It depends on the microprocessor design. Integrated execution units, most common today. Description: FP and Neon are part of the main CPU core and handled by the dedicated execution units. Okay, inside the main core, there are different units which act as a floating point unit and neon unit, SIMD unit. Separate coprocessors, old ARM design, some DSPs, data signal processing. FP and neon are separate processors that the main CPU communicates with. Okay, example, Apple's ARM-based M1 main CPU handles a general purpose integer operations, floating point and neon units. Integrated into the CPU executes FP and SIMD in parallel. Neural engine separate hardware for AI tasks. How do software and compilers use these units? General purpose code runs on the main processor. Floating point operations automatically go to the FPU. SIMD instructions neon are used when explicitly optimized. Example compiler flags like this neon OS and compilers schedule introductions efficiently to utilize available execution units. OS and compilers schedule instructions efficiently to utilize this. Final answer, yes, there is one processor. Okay, so now in the modern ARM processors, there is the general purpose unit inside the processor, and then there are two other units, one floating point unit and other SIMD, and these have their own separate set of registers and instructions, and are used whenever instructions are given to them. hmm, to them. So when writing in assembly, do my instructions for floating point and neon go first to the general purpose core, and it passes them on to the uh, these other units. Let's see, that is exactly how it works in modern ARM processors. Let's go rocket. Breakdown of execution flow in modern ARM processors. ARM processors is structure simplified. General purpose integer unit execution executes integer operations. Memory access branches, and this floating point executes floating point number. Use these registers, also use these registers but in vector format. Neon and this. All three units are part of the same processor, but each has dedicated execution resources. Okay, how assembly instructions are handled. When writing a ARM64 assembly, your FP and Neon instructions go through the general purpose pipeline first before being dispatched to the appropriate execution unit. Execution flow. Instruction fetch and decode done by the CPU frontend. CPU fetches assembly instructions including FP and Neon in ones, decodes which unit should execute each instruction. Instruction dispatch sent to execution units. Integer instruction go to integer execution unit. FP instruction go to FPU, and Neon instructions go to Neon SIMD unit. Execution parallel processing. Different units execute instructions in parallel if possible. Results are stored back in respective registers. Assembly code example. Here is an RN assembly snippet mixing integer, floating point, and SIMD instructions. Add this and this. This is general purpose. FAAT. This, and this. This is just like opening a multiverse. I have been doing this, but now I can do this and this. All of these new instructions. That is just crazy. What happens internally? Add this and this execution in the integer ALU. Yes, in the integer ALU. I have an ALU. These do not happen in the control unit. Yep. Instruction fetching and decoding happens in the control unit, but the execution can happen in different units. If it is a load or store operation, then it is handled by the control unit. But if it is not, then like if it is some multiplication, division, addition, subtraction, then it is sent off to the ALU, FPU, or neon unit, depending on the instruction. The CPU schedules these based on availability, often running integer and SIMD operations in parallel. Does the general purpose core forward instructions? Yes, but only in the sense of scheduling. The general purpose core does not execute FP or neon instructions itself. It just executes them and decodes them and sends them to the correct execution unit. Think of it as a traffic controller. The CPU core fetches the instructions and decides where they should go. Each execution unit processes its own instructions independently. Yep. Performance considerations. Since FPU and Neon units work in parallel with the main core, efficient scheduling can speed up performance. Instruction dependencies can use stall. Example, if the FPU is waiting for an integer result before executing, compilers often reorder instructions to minimize delays. Okay. Final answer, yes. FP and Neon instructions go through CPU first, which dispatches them to the correct execution unit. General purpose core does not execute FP or Neon instructions, it just schedules them. Parallel execution happens when possible, improving efficiency. And now, the unit for floating point arithmetic is is normally called is called floating point unit, which seems obvious, but why? But what does neon mean, and how is it related related to single instruction multiple data? What is neon in ARM? Neon is ARM's single instruction multiple data architecture extension for accelerating vectorized operations. It has not been 2 hours, but I will have to go to the washroom. Just, I will be back in a minute. Let me mute myself. Yep, me back. Is it lagging? Nope, I don't know. Frames have been dropped. 206 frames have dropped. But yeah, that is cool. Now, this is becoming fun again. It is like we are learning assembly from the start again. Yes. What is Neon in ARM? Neon is ARM's SIMD single instruction multiple data architecture extension for accelerating vectorized operations. Okay. What are vectorized operations? Neon stands for Advanced SIMD Neon Technology. Neon stands for Advanced SIMD Neon Technology. It doesn't have a full acronym, it's just a branding name by ARM. How can Neon stand for this? Shit. How is Neon related to SIMD? SIMD single instruction multiple data set means that a single instruction operation on multiple pieces of data at once. Neon implements SIMD by allowing parallel processing of multiple values using 128-bit vector registers. Example, scalar versus SIMD without Neon scalar execution. I load value from this into this and then from this into this and add and store the result in this and then store back the result in memory. Each operation executes one by one. With Neon SAMD, I can load and then add, load four values into this, load four values into this, the same as this, and then add four elements at once. What the heck? How am I adding four elements and then I am storing processes four values in parallel? Okay, because it is loading four elements at once. Okay, that is crazy. Neon features 128-bit vector registers can can operate on 16, 8, 26, 64-bit values, parallel execution of arithmetic and logical operations, speed of image processing, multiple multimedia AI combination. Neon equals ARMS SIMD. What does vector mean here? Is it just 128-bit values or vectors are some concept which is represented as 128-bit values here in SIMDs? What does vector mean in Neon and SIMD? Why is there a and in between? It should be Neon SIMD, right? In the context of SIMD, single instruction multiple data vector is a data structure that holds multiple values, allowing a single instruction to operate on all elements at once. In the context of SIMD, a vector is a data structure that holds multiple values. Okay, a vector is a data structure that holds multiple values. Like, and a vector can hold magnitude and direction, right? Multiple values, allowing a single instruction to operate on all elements at once. A vector in Neon is simply a collection of multiple smaller values stored in a single 128-bit register. Okay, that makes sense. Vector and scalar. Vector, a single value is stored in a register, like some variable equal to 42, like here, or something. But a vector can store multiple values. Ah, vector, single instruction, multiple data. Okay, that makes more sense. Are vectors just 128-bit values? Yes, but the key idea is how they are interpreted. A 128-bit vector is not just one value, it contains multiple smaller values. The size of each element in the vector is this: V0 16-bit, half bit, 4 single bits, 2 16 8-bit numbers, or 8 16-bit numbers, or 4 word 32-bit floats, or uh, 2 2D 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 add this and this, adds this and stores into this, adds 4 single bits to 4 single bits from this register and stores them to 4 single bits in this register. That is crazy. Means this plus this and adds them individually. 10 plus 1, 11, and all that crazy stuff. Okay, SIMD instruction does all 4 at once. Hmm. Hmm. Neon is a subset of SIMD, but SIMD is not a subset of Neon. Neon is a subset of SIMD. That's it. Yes, Neon is a subset of inside SIMD in the sense that it is ARM's specific implementation of SIMD. SIMD is a concept, and uh, SIMD is a concept, and Neon is an implementation. No, Neon is not an implementation. It's a concept, and Neon is a standard which is based upon that concept, and then it is implemented by processor manufacturers. Yes, exactly. Here is how it works step by step. SIMD is a concept theory. SIMD, single instruction multiple data, is a general computing concept. It means that one instruction operates on multiple data points in parallel. SIMD is useful for tasks like graphic audio processing. Neon is a standard space. GPU is a very better SIMD, I guess. Hardware for SIMD, which takes SIMD to its limits. Neon is a standard specification. Neon in ARM64 implementation of SIMD. ARM defines a standard instruction plus register layout. Neon is ARM's implementation of SIMD. ARM defines a standard instruction plus register layout for how SIMD operations should work in its architecture. This standard includes 128-bit registers, 32 of them, instructions like this, operations on all 32-bit values at once. Other instructions have their own SIMD. Intel and AMD, not ARM, AMD have SSE, AVX 512-bit. So that is crazy. PowerPC have this, and RISC-V has RVV, RISC-V vector extension. Hmm. Okay. Processor manufacturers implement Neon in hardware. Once ARM defines the Neon standard, chip manufacturers Qualcomm, Apple, Samsung also makes chips, so Samsung does not use Snapdragon from Qualcomm implementation. It is their actual hardware design. This means all ARM processors with Neon support will have hardware units that execute Neon instructions efficiently. What do I want to ask now? Okay, things make sense. Yeah, yes, about GPU. So are GPUs dedicated hardware units which take SIMD to a very serious level? I guess yes, GPUs are to which take SIMD to its extreme. How GPUs related to SIMD? SIMD is the foundation. SIMD allows one instruction to process multiple data points. Neon is ARM's implementation. And GPUs take SIMD much further. While CPUs use SIMD for small scale parallelism, GPUs are designed for massive parallelism. A GPU can have thousands of tiny processing cores, each running SIMD operations simultaneously. This makes GPUs ideal for graphics rendering, AI, specific computation, and cryptography. Key differences between GPU and SIMD units. Between GPUs and CPU SIMD. Parallelism, limited, few ALUs per core, massive, thousands of cores, few ALUs per core. Okay. Execution model, SIMD, single instruction on multiple data points, SIMT, single instruction and multiple threads. Threads, that is operations being divided into parallel micro operations which are which take place in different cores, which execute in different cores, similar to SMD but across multiple threads. Okay, what is threads? Use cases, general purpose computing. Hmm. Graphics, AI, deep learning, it just takes it. GPUs take CPU with SIMD to its extreme limit, I guess. Memory access, fast, low latency, high bandwidth with higher latency, but higher latency. CPM, SIMD, and GPU parallelism aspects. Registers, 128-bit registers, many small registers per thread, and each thread goes through one core, and they have thousands of cores, thousands of GPU cores, 4 to 16 cores. Execution, SIMD, small scale parallelism, large scale parallelism. SIMT, single instruction, multiple threads. Task type, short vectorized maths, massive parallel workload. Threads. What are threads? Are these instructions? Are these programs which run? Are thread? What are threads? Do they mean up? Do they refer to a program which is being executed on a core, and multiple and multiple threads mean that different programs are running on different cores. Different programs are running on different cores, and each program has its own set of instructions, and this is different from SIMD in the sense that SIMD has multiple has a single instruction which runs in a single processing unit, but that processing unit has multiple data points, but SIMT takes in instruction, and that is broken into different into smaller parts and sent through multiple processing units at once with multiple but different data points. Is that correct? Yes, you are getting it. Let's break it down carefully. What are threads? A thread is a sequence of instructions that a processor executes. A program can have one or multiple threads. Oh, a sequence of instructions. A program can have one or multiple threads. Okay. If multiple threads exist, they can run in parallel on multiple cores or be time shared on a single core Threads versus cores. Thread is the pro set of instructions that run, and core is the hardware where it runs. A single execution or a single sequence of executed instructions, a lightweight processing core, a physical processing unit inside a CPU can execute multiple threads, either by having multiple cores or by time sharing. Multiple threading, running multiple threads on one or more cores. Multiprocessing, running multiple programs across multiple cores. Okay. How SIMD is different from multi-threading. One instruction operates on multiple data points at once. Each thread has its own instruction stream. Yes. Execution unit runs on a single processing unit, runs on separate cores or logical units. Okay. Parallelism type, data parallelism, same operation on different datas. Task parallelism, different operations in parallel. Yep. The operations also can differ. Neon, this adds 432-bit values, two browsers running tabs, different code on different cores. Okay, so multi-threading is about running different sequences of instructions, while SIMD is about running the same instruction on multiple data points at once. That makes sense. How SIMD GPU execution model is different from SIMD. Single instruction, multiple threads is like SIMD but at a massive scale. It uses GPUs where one instruction is sent to many parallel threads, unlike SIMD where one processing unit works on multiple data points. SIMD runs multiple threads that each process their own piece of data. Execution model. One instruction operates on multiple data points at once. One instruction is issued to multiple threads running on separate units. Yep, hardware. A CPU execution unit, Neon and ARM. Thousands of GPU cores, thousands of GPU cores, each running on a thread. Flexibility. All data points must follow the same instruction. Threads can take different paths with some efficiency loss. Example this, and NVIDIA CUDA launches thousands of threads for matrix multiplication. Hmm. What else do I not understand? There was one point here. If a program can run on one or more threads, okay, single program can instruct different cores or a single core to do multiple to execute different sets of instructions either either on a single core by time sharing or multiple cores in parallel, and multi-threading, running multiple threads on one or more cores, running multiple programs across multiple cores. Yep, that makes sense. And I guess that is the end of today's stream, and tomorrow we will start with this chapter, floating point, so that we can learn what the heck is going on with these and learn new assembly instructions. That is crazy. And bye for today.